This is Algebra 2, Unit 8, Lesson 6, and in this lesson we're going to learn about inverse functions and how to find them. Your first introduction to inverses was when you were working in Algebra 1 with relations, or a set of ordered pairs. And when you have a relation, you learned things like what is the domain. That was your first introduction to the domain is a list of the x's, your range is a list of the y's. And then another thing that we talked about is whether it was a function or not. If the x repeated, it's not a function. If it doesn't repeat, it is, and things like that. But then we talked about inverse functions. The inverse of a function is when you switch the x and the y coordinate. So if I have a relation like this and I want the inverse of that relation, well, it's still going to be a relation. I still put it in set symbols, but the inverse of that relation is just going to be where I switch all of the x and y coordinates. So the inverse of this relation would be 1, 2, 1, 5, and -4, 2. And so we're going to extend that thinking today on how do we deal with inverse functions if those functions are written algebraically. Another thing you need to understand in dealing with functions and relations when they're graphed is you need to understand what happens to the graph of that function. So I took those same 3 ordered pairs and I graphed them here. And I did those ordered pairs on purpose that way. I want to draw those ordered pairs so that it makes a right triangle, so that you can see the relationship between those 3 ordered pairs and what happens. So if I just take these ordered pairs, 2, 1, and I switch it and make it 1, 2, I'm going to graph the inverse relation in a different color so you can see the difference. So the inverse of the point 2, 1 is 1, 2. So I'm going to graph that 1, 2. The inverse of 5, 1 is 1, 5. So 1, 5. The inverse of 2, -4 is -4, 2. And so I'm going to connect those ordered pairs like I did the ones in the original relation. And look at that. Notice this is a right angle and this is a right angle. So that relation, those ordered pairs have flipped, if you notice. And where they flip is across this y equals x line, and that is always going to happen when you're talking about inverse relations. They will always be, if they are true inverses, they will be symmetrical about that y equals x line, which becomes very significant if you're trying to identify functions that are inverses. If they give you a graph and they ask you to identify the inverse, well, all you have to do is take points from that graph and flip them and see which graph matches those points that have been flipped. It's really pretty simple to do, but if you've never seen it this way, it makes it very difficult. So the ordered pairs in the graph, if you just flip their x and y values, switch their x and y values, those inverse functions will always lie across the y equals x line. And if I give you this function and ask you to find its inverse, or if I give you this triangle and ask you to find the triangle that would be its inverse, all I have to do is take the ordered pairs, this is 5, 1, and flip it to 1, 5. Take this ordered pair 2, 1 and flip it to 1, 2. Take this ordered pair 2, -4 and flip it to -4, 2. And I will have the inverse of that function graph. The next thing we need to talk about is the notation associated with inverse functions. If my original function is f of x, you understand that the f of x is the same thing as y, okay? But the inverse function, the notation for the inverse of f of x is f negative, the inverse of g of x would be g -1x, the inverse of g. The inverse of h of x would be h -1 of x. That does not mean it's h to the -1 power. That means this function is the inverse of the h function. This function is the inverse of the g function, and this function is the inverse of the f function. When you're given functions in algebraic form, to find the inverse of those functions, it's really simple to do. Basically, we know that f of x is y, g of x is y, h of x is y. Any function notation, anytime you have f of x or any letter of x, we know that that's the same thing as y. So the first thing I'm going to do is I'm going to replace the function notation with y. So y equals 2x plus 4 is the same function that we had here. We've just changed what it looked like. The next step is I'm going to switch. Remember, to find the inverse of a function, we swap x and y. So that's what I'm going to do. I'm going to switch x and y. So instead of a y here, I'm going to exchange that with an x. And over here, instead of x, I'm going to exchange that with a y. So I switch the x and y in my equation. And then the next thing I have to do is solve that equation for y. I got to get y by itself. So when I do that, I have x minus 4 equals 2y. Then I'm going to divide by 2. So x minus 4 divided by 2 equals y. And now I'm going to replace y with the inverse function notation, because remember, this is not y equals, this is the inverse of the original f of x function. So instead of putting y there, I'm going to write that as f negative 1 of x. The inverse of f of x is equal to, and I'm going to write that, I could leave it like this, x minus 4 over 2. I could write it in slope-intercept form. It just depends on what book you're working out of or the website you're looking at as to how they want you to express that answer. But I would accept either of those. They are both perfectly fine. But the main thing here you need to understand is y is the inverse of the f function. That's why I need the f of negative 1 of x. The inverse of f is 1/2 x minus 2. Let's do this one, and we're going to find the inverse of g of x. Just like before, g of x is the same thing as y, so I'm going to replace it with y. Then I'm going to switch x and y, so x equals y squared plus 7. Then I'm going to solve for y. So x minus 7 equals y squared. To solve for that, I take the square root of both sides. So the square root of x minus 7 is equal to y. So the inverse of that function is the inverse of g is equal to the square root of x minus 7. For this one, since we're talking about the inverse of g being a function, we do not need the plus minus symbol here, because if you think about what that function would look like if it is symmetrical about the y equals x line. The original function is a parabola that's facing up. If I flip that across the y equals x line, when it's flipped across the y equals x line, and I don't know where it's going to be, but if I flip that function across this, isn't it going to look something like that? And if it looks something like that, it's no longer a function. So we can only consider the positive portion of this. We're not going to consider the negative, because if we do, it's not a function any longer. So that's why I don't need the plus minus here. So don't be confused about that. When we take the inverse functions, if we put in the square root, we only need to consider the positive values, because otherwise it's no longer a function if we don't. Here, I want to find the inverse of h of x. The first thing I'm going to do is replace h of x with y. That equals x cubed minus 8. I'm going to switch x and y. So x equals y cubed minus 8. Then I'm going to get y by itself. X plus 8 equals y cubed. And then I'm going to take the cube root of both sides to get rid of the cube there. So y equals the cube root of x plus 8. And so that's the inverse of the h function. So h of negative 1x, the inverse of h, is equal to the cube root of x plus 8. The next important thing you need to know about inverse functions is, if two functions are inverses, then their composite functions when put together will be equal to x. So if f and g are functions and they are inverses, then f of g of x, when we plug the g function into the f function, we will get x. And when we plug the f function into the g function, we will get x. If that happens, then we know the functions are inverses. So another way they might ask you about inverses is they may give you two functions and they may say, are these two functions inverses? Well, there are a couple different ways you could do this. You could use the old method. You could take this function, f of x. I'm going to replace f of x with y. So I've got y equals 3/4 x minus 6. And then I'm going to swap the x and the y. And then I'm going to get y by itself. I'm going to add the 6 over. and then I'm going to multiply by 4/3. And then I'm going to replace the y with the inverse. F negative 1 of x is equal to 4/3 x plus 4/3 times 6 would be 8. If they ask, are these two inverses? Well, that looks like no, they're not, because they are not going, that does not give me the same thing as g of x. So here, I'm asking the same question. Are f of x equals 1/2 x plus 6 and g of x equals 2x minus 12 inverses? Well, I could do that by finding the inverse of 1 and seeing if it matches. That's one way to do it. Or I could follow this. I could plug the g function into the f and see if I get x, and then plug the f function into the g and see if I get x. If I get x for both of those, then they will be inverses. So let's do that. F of g of x. Well, that means I'm going to plug the g function into the f function. So I'm going to take the 2x minus 12. Everywhere there's an x in the f function, I will replace it with 2x minus 12. So that would be 1/2 times 2x minus 12 plus 6. And then I'm going to do the math. 1/2 times 2x is x. 1/2 times 12 is negative 6. Or it's minus 6. 1/2 times negative 12 is negative 6 plus 6. So that gives me x. So far, yes, it looks like they're inverses. Then I'm going to do the opposite. G of f of x. Here, everywhere I have an x in the g function, I'm going to replace with the f function. So I have 2 times 1/2 x plus 6 minus 12. If I do the math, 2 times 1/2 x is x. 2 times 6 is 12. Minus 12 does give me x. So yes, these two functions are inverses because the composite function f of g of x is equal to x and g of f of x is equal to x.